Welcome. My name is Andreas Quirrenbach. I'm at the University of Heidelberg, and I am going to talk about the fundamentals of instrumentation. When I say fundamentals of instrumentation, I really mean the working principles of the instruments that we use to do radial velocity surveys of stars to find extrasolar planets. And this type of instrument is called a cross-dispersed Echelle spectrograph. So to understand what that is and how it works, let's first look at the layout of a basic grating spectrograph. Light enters from the telescope, is collimated into a parallel beam, then dispersed at a grating, and in the end the light is collected by a camera, and then a spectrum is generated on the detector. A grating is nothing else than a regular pattern of grooves, which here have a separation that we call sigma. The most fundamental relation for such a grating is the so-called grating equation. The grating equation is the condition that adjacent beams, or the rays coming from adjacent grooves, have a path length difference that is an integer multiple of the wavelength. Then you get constructive interference between these adjacent rays, and you see the wavelength imaged into that direction. From the grating equation, we can immediately derive the so-called angular dispersion, that is the spread of the spectrum on the detector, by just differentiating the exit angle with respect to the wavelength. From that dispersion equation, we can calculate a very important quantity, and that is the resolution of the spectrograph. The spectrograph images a spectral line onto the detector, and you can calculate the width of that image and compare that to the separation of two adjacent lines that are separated by a wavelength difference delta lambda. You take that directional difference from the angular dispersion direction, equate that to the width of the image, and then you get a relation describing the resolution of the spectrograph. That is to say that if you have two lines that are separated by an amount delta lambda in wavelength, they are identifiable as separate lines in your spectrum. So in this relation, describing the resolution, which is defined as lambda over delta lambda, we see that this relation contains the length of the grating, which is the dimension of the grating in the direction orthogonal to each one of the grooves. It depends on the order of the diffraction. It depends on the size of the angular slit or the fiber with which you couple light into the spectrograph. It depends also on the telescope diameter. And the ratio of W and sigma is also the total number of grating lines that are illuminated. So this relation that describes the resolution of the spectrograph has very important consequences for the design. So first of all, let's take a look at a few typical spectra of stars. These are spectra on the top of an A star and then of some M stars further down. And what you can immediately see is that the spectra of the cool stars have a large number of sharp lines. And to take advantage of these sharp lines for radial velocity measurements, we want to construct a spectrograph that can actually resolve these lines. So the intrinsic resolution that you want in your spectrograph is determined by the spectrum of the star that you want to observe, or in other words, you can take advantage of the information in the spectrum only if you can resolve these lines. So if you calculate the radial velocity precision that you can get and do that for different spectrograph resolution and for stars with different rotational broadening of the lines, you get curves like these. So let's take a low resolution spectrograph at 20,000. It follows this curve. So up to the right, the rotational broadening of the lines is large, and really it doesn't matter very much what the resolution of your spectrograph is. Then if you go further to the left where the lines are narrower, you see now that the precision that you get by the spectrograph is determined by the spectrograph resolution. And in this regime, where the rotational broadening is small, you can gain substantially by going to higher resolution. So building spectrographs for Doppler measurements means normally you want to push for high spectral resolution. You get the best radial velocity precision typically with spectrographs of a resolution of at least about 80,000. So I repeat here the equation that we had derived previously that describes the resolution as a function of the spectrograph parameters. So we can see here that if we want high resolution, we can do that if we have a large spectral order M and a large grating, which gives us a large number of illuminated lines, or equivalently the ratio W divided by sigma, so W being the size of the grating, should be large. We also see that a larger telescope means we need a larger spectrograph. The size of the grating that we need, W, is proportional to the size of the telescope. Building high resolution spectrographs for large telescopes is much more difficult than building spectrographs for smaller telescopes. Furthermore, we see that a smaller slit, and that is calculated in arc seconds on the sky, means we can use a smaller spectrograph. Sites that have good seeing are better. You can try to narrow the slit further, but if you make it smaller than the seeing disk, then you lose light, and normally you don't want to do that. So typically, the spectrograph slit size or fiber size should be about the size of a seeing disk. There's a trick that you can play, and that is image slicing. So you can slice the image of a star in two, so it looks like two half moons, and put them on top of each other. And this cut and stack of the star image, if you do it in two slices, gains you a factor of 2 in spectrograph size. There's an attractive alternative, and that is to use adaptive optics, because adaptive optics means that you restore the refraction limit of the telescope, and the size of the entrance of the spectrograph that you can use is of the order lambda divided by d. That is the optimum, and that is typically a factor of at least maybe 20 or so smaller than the size that you can use in a seeing limited spectrograph. So there's a big advantage if you can work with a diffraction limited spectrograph, but then you have to have an excellent adaptive optics system, especially in the visible, that is difficult. So here's an image of the interior of one such spectrograph. It's the near-infrared spectrograph of the CARMEN-S instrument. And in the front, you see the grating. This is the grating that is used in that spectrograph. And it is a very large grating. And this is, in a visible light spectrograph, typically the most expensive optical part. In a near-infrared spectrograph, the detector may be more expensive than the grating, but these gratings are expensive and difficult to make. So making your spectrograph as small as possible is important, but you are normally limited by these fundamental relations that I discussed before in how small you can possibly make a spectrograph. Now this is a picture showing the vacuum tank of the CARMEN-S instrument. And here again, you can see the instruments are relatively small, large, and that is driven by the size of the telescope and the high resolution that you want. There is no way really around this equation. So coming back to the grating geometry, this is again to define the quantities that we will be using. D1 and D2 are the beam sizes before and after the beam gets to the grating. W is the length of the grating, alpha and beta, the grating angles. Normally we use these gratings in a configuration in which the angle alpha is about the same as beta. The reflection is more or less symmetric, and this configuration is called the Littrow configuration. This can, of course, exactly be true only for one wavelength, but we typically want our instrument to work such that this condition is fulfilled somewhere in the middle of the spectrum or the middle of the detector. So in that case, the equations get a little bit simpler, and alpha equals beta, and then we have these relations. The resolution is given by 2 times the beam size before the beam gets to the grating, divided by the slit size in arc seconds, divided by the telescope diameter, times the tangent of that angle beta. Here I give some typical values to give you an idea of what these values may be in a realistic instrument. So 8,000 angstroms is somewhere in the middle of the wavelength range of the CARMEN-S spectrograph. And here we work with a 77th order of the grating. The grating has 31.6 lines per millimeter. The beam size is about 15 centimeters. And the grating is used at an angle for which the tangent of the angle equals 4. So that means the width is 15 centimeters, but the length of the grating, you saw that on the picture that it is very much longer than it is wide. The length is 60 centimeters. The projected fiber size on the sky is about 1.5 arc seconds, and that is sliced into 2. So that's shown here on the right. So you see half of the image of the fiber is here, and the other half is here, and they are stacked on top of each other. So this is the dispersion direction, and in the dispersion direction, the image now is only half the size of what it would be if you didn't use this trick of slicing. We are at a 3.5 meter telescope, and that gives us a resolution of a little more than 90,000. So if you want to use a similar instrument, say at an 8 or 10 meter telescope, you would either have to make it 3 times bigger, or you would have to make the entrance fiber smaller on the sky. So if you had a site that has better typical seeing, you may be able to afford that. Or you would have to apply more slices. You can try to cut your star image into 3 pieces instead of 2, for instance, and gain a little bit by that. But from these numbers, you see that you are very much constrained in the construction of such instruments by the high resolution and the large telescope size. So the next question is, how much light do we actually get into our spectrum? And unfortunately, if you take a grating in a simple-minded form that I showed before, it acts mostly as a mirror and sends out light, just all the light into the 0th order, where you don't get a spread spectrum. So some of the light is diffracted also into the higher orders, but you get this envelope, and the width of the envelope is just given by the wavelength divided by the slit width, or the groove width, I should say. You have many grooves on the grating, and that gives you the envelope. So the usable orders are these orders where you really get out a spread out spectrum, and they don't receive much light. So to get around that, one can use a so-called blazed grating, in which the reflecting surfaces are tilted with respect to the actual bulk, large-scale direction of the grating. And then it acts essentially as a mirror that sends the light out mostly in the direction, in a higher order. And that is nice, because then you get most of the light really where you want it. Gratings that are blazed are called echelettes if they are used in low order, or echelles if they are used in high order. So here, this figure shows the blaze function for 3 orders. This is a grating, and it shows the angle alpha plus beta on the x-axis, shows the intensity that goes into a certain direction for the 1st, 2nd, and 3rd order. So one sees here that the efficiency of the grating is optimum in that blaze direction, but it deteriorates in the direction that is off from that blaze direction. If you plot the same curves against wavelength, you get these 3 curves. So if you take your wavelength as the x-axis, the efficiency of the spectrograph will vary with that wavelength. That is an important property of all echelettes and echelles. So if you have an echelle that really works in high order, the blaze function in litho configuration looks like this. You get an oscillating efficiency as a function of the wavelength. And if in later talks you see flat spectra, then probably they were taken with an echelle spectrograph, but then in the data reduction, at some point, there was a division by that blaze function. That is a typical step in the data reduction from echelle spectrographs. You still, of course, have a variation of the signal-to-noise ratio with wavelength. Wherever the efficiency is high at the peak of the blaze function, you get higher signal-to-noise than you get at the edges. So now let's look at this in a bit more detail. What happens to the different orders? So schematically here, we see that in one direction, this is a constant alpha beta. 3 orders may fall on top of each other. You get light from the 1st order, from the 2nd order, and from the 3rd order at different wavelengths. The 1st order at 9,000 angstroms, the 2nd order at 4,500, the 3rd order at 3,000, all are reflected into the same direction. That was evident also from the plot of the blaze function against angle. So if you show this schematically here for an Echelle, you have all the orders here, 99, 100, 101, 102, going into the same direction. So this is shown schematically, but in reality, what you see on your detector looks like this. The different orders are placed on top of each other because they all go into the same direction. They correspond to different wavelengths. So in your spectrum, you get different wavelengths placed on top of each other. Clearly, you don't want that. So what is required in a spectrograph, especially working in these high orders, is order sorting. If you take no measures, then the different orders fall on the same pixel for different wavelengths. And you can now either take a bandpass filter, so you filter out one of the orders and reject all the others, and then you have the desired wavelength range on your detector, but you have rejected everything else. For an Echelle grating, that means you can record only a small wavelength range because the overlap between adjacent orders, the so-called free spectral range, in which is the range from where the nth order overlaps with n-1 to where it overlaps with n+1, this spectral range is relatively small. If you want to record a large spectral section in one shot, you can use what is called cross dispersion. The cross dispersion principle works with two dispersing elements. So here we have the ray coming in from the telescope. Here's our Echelle grating. We create overlapping orders here. And now we have a cross disperser which introduces dispersion in the orthogonal direction. So the orders get separated in the other direction. This is along the order. These are now the separate orders. So by having two crossed dispersing elements, one can record a large section of spectrum. So you record many orders simultaneously on a rectangular detector format. So then this is the basic layout for a cross-dispersed spectrograph. You have again the ray from the telescope entering here, being collimated, sent to the grating. Now here you create the dispersion in one direction, so the light starts out spreading spectrally, and here you have the cross-disperser dispersing in the other direction, so that in the end your camera records this two-dimensional format, which is shown here. So here we have dimensions in millimeters. So this is in the focal plane of the spectrograph camera. And here we see that each order runs in this direction. And here you have the order numbers. So starting at the lower numbers in the red to the higher numbers in the blue. Here are the corresponding wavelengths. And now you can place a detector in this plane and catch the light from many orders. You also see here that you need a fairly large detector to catch the whole visible spectrum. This is a very old picture here. This was an 800 by 800 pixel detector that could capture only a small section of the spectrum. In a modern spectrograph, you may have a 4K by 4K detector, which then can collect the light from the whole visible light. So after some data reduction, you get a spectrum, a two-dimensional spectrum that may look like this. This is a solar spectrum taken with an Echelle. And as I mentioned before, the data reduction here has already flattened the individual orders. So on the detector, you would see that the spectrum is much brighter here than at the edges. So each one of these spectra, you have the underlying Blaise function, but that was taken out by dividing by the Blaise function. And then, of course, the artist here colored it. And you see that you can get a large section of the spectrum with high resolution, get a lot of information on one single Echelle exposure. So at this point, I should also mention this very good book by Schroeder about astronomical optics. So if you want to read a little bit more about the derivation of the equations that I showed, many of the images that I showed were taken from this book. I highly recommend looking into this book. It's a very good introduction into the optics of telescopes and spectrographs. So now I would like to talk a little bit about the fundamental limit for the radial velocity precision. We are all interested in finding small planets, which means doing radial velocity observations with very high precision. So I frequently get asked a question which runs something like this. We saw that the typical spectrograph resolution is about 100,000. And that makes sense because the broadening of stellar lines is typically a few kilometers per second. So resolution of 100,000 corresponds to a Doppler velocity of about 3 kilometers per second. So that's the typical line width of a star. So you just resolve the stellar lines, but you don't over-resolve them. But now you have an instrument that has a resolution of 3 kilometers per second, but we can use it to measure Doppler shifts that have an amplitude of about 1 meter per second. So how is that possible? That looks confusing at first. So here, we really have to make the distinction of the resolution of a spectrograph, which is the ability to separate adjacent lines and clearly see that there are 2 lines and not 1, from a different question. And the different question is, how precisely can I measure the location of a line? So what we actually measure in the spectrum are counts in pixels. Very fundamentally, we measure how many photons hit each pixel of the spectrograph. And this is a quantity that we then can plot along the x-axis here, say, which may be the wavelength or the pixel number. And then if you want to know the position of a spectral line, what we do is typically we fit a line to the data points. And now, of course, in this line fit, there is an uncertainty. So this may be also an acceptable fit to the line, or this may also be an acceptable fit. So intrinsically, because your data points have some noise, there is an uncertainty, which I call small delta x, in the determination of the position of this line. Now, let's assume we took data with smaller error bars. So again, we fit a line, and now the uncertainty in having other fits that also might fit the data points, but the spread between these, the uncertainty of the measurement, small delta x, is smaller. So it's very important to realize that the precision with which one can center a line depends on the size of the error bars for each data point that went into this measurement of the line. To make this more quantitative, the measurement precision delta x is about the full width half maximum of the line divided by the signal to noise ratio. So the signal to noise ratio is the depth of the line divided by the size of the error bars. So this formula is an approximate one, and the exact factor that goes in front of this ratio, full width half maximum divided by signal to noise ratio, depends on the line shape, but within a factor that is not that much different from 1, this is an extremely important relation that applies to all kinds of different measurements. Whenever you measure a line in a spectrum or want to position or measure the position of a star on a detector or something that is similar, this formula should guide you. And the fundamental limit, of course, is the photonoise limit. You cannot get better than the limit that is given by the noise that you get from counting photons and the stochastic nature of photons. So the signal to noise ratio is the square root of the number of photons that you gather. If you gather n photons, the width of the distribution is square root of n, so the signal to noise ratio is the square root of n. This is basically the fundamental limit for measuring the position of a spectral line. Or another example would be the Gaia satellite. I don't know whether you ever wondered about it. The resolution of the Gaia satellite is about 0.1 arcsecond, which is roughly the resolution of a 1-meter telescope in space. But the quoted astrometric precision is something like 20 microarcseconds. So how does that fit together? Exactly by this argument. If you have a sufficient number of photons, you get a high signal to noise ratio, and then you divide your 100 milliarcseconds by a large factor to get down to 20 microarcseconds for the astrometric precision of the Gaia satellite. And actually, over a large range in stellar brightness, for any stellar brightness down from about 12 magnitude, the Gaia satellite precision can very easily be calculated from this photonoise limited performance. And the same applies to Doppler spectroscopy. So the small delta V, the uncertainty in centroiding a spectral line, is given roughly by the delta V divided by the signal to noise ratio, the capital delta V divided by the signal to noise ratio, and that is the speed of light divided by the resolution of the spectrograph times the signal to noise ratio. So now if you take a spectrograph that has a resolution of 100,000 and you get a spectrum with a signal to noise ratio of 100, this gives a Doppler precision of about 30 meters per second. 100 is typical for the exposures that we take. So 30 meters per second sounds a lot better than 3 kilometers per second, but it's still not, of course, what we want. So there's a second factor that helps you, and that is you have to take into account the spectral information content. So stellar spectra, as I showed, have many spectral lines. And each of these lines provides a statistically independent measurement of the stellar radial velocity. So in one spectrum that has n lines, you can make n measurements of the radial velocity, so that further reduces the uncertainty by a factor of square root of n. Now in practice, you don't do that. You don't separate a large number of lines, but you do something like a calculation of a correlation function. And to quantify that, you can aggregate the amount of spectral information in a factor that is frequently designated with a capital Q. So now the radial velocity precision is speed of light divided by that Q factor times the signal to noise ratio. And that Q factor now captures the information that is in the spectrum. So it depends on the number of spectral lines that you have. It depends on the depth of these spectral lines. It depends on the resolution of the spectrograph. And it depends on the stellar input spectrum. So, but if you take a typical number, again, say, making this very simple-minded argument that your spectrum may have 1,000 lines, you make it 1,000 independent measurements of the radial velocity, that would get you down from the 30 meters per second to 1 meter per second. I say, to make this more quantitative, you have to calculate this quality factor, and that quality factor is shown in this view graph for different stellar types and for different rotational velocities. And here on the x-axis, we have the spectral resolution of the spectrograph. So we see that a star that does not rotate, these three are stars that don't rotate, a late type star has more spectral lines than an early type star. So this has higher information content and therefore higher quality factor. If the star rotates, you smear out those lines, and that reduces the quality factor. And again, you have to match the spectral resolution of your spectrograph to this information content. If you have a rapidly rotating star, it doesn't matter very much because the lines are broad anyway. But if you have a slowly rotating star, then you can gain by going to higher spectral resolution. So here would be our typical R equal 100,000 spectrograph. So this is the fundamental limit. But now you also have to realize this in a real world instrument. So that is the question about spectrograph stability and calibration. So to illustrate this, 1 meter per second radial velocity precision typically corresponds to 1/1000th of a detector pixel. Or this is about 15 nanometers, which is about 30 silicon atoms. So you shift your spectral lines by 30 silicon atoms, and you have a signal of 1 meter per second. Or in other words, if something inside your spectrograph, if the detector shifts by 30 silicon atoms with respect to the incoming beam, you also get a fake radial velocity signal. In the fundamental limit, the photonoise limit, you have the advantage that you can average over many lines. And as long as we talk about photons, these are independent and give you independent measures of the radial velocity. But if you shift the detector as a whole, then of course you shift all the lines and you cannot take this averaging argument anymore. So in the spectrograph calibration and stability, you really have to get down to this 1/1000th of a detector pixel or even better requirement. So you need extreme instrument stability, which means you typically take a vacuum to eliminate pressure fluctuations. You use high thermal stability, typically on the millikelvin level, to make sure that your optical elements don't shift, your optical bench doesn't expand, and so on. You normally ban all moving parts from the inside of your spectrograph. You want undisturbed operation, so you put your spectrograph up on the telescope, you make sure it works, and then you lock the door. Nobody is allowed to enter, and you open the door again 10 years later after you're done with your survey, in an ideal world. And of course, to avoid any differences between your observation and the calibration, you do that simultaneously. So it's really impossible to build an instrument that doesn't shift by 15 nanometers. That would be way too demanding. So what you typically do is you inject calibration light from a very stable source and observe the calibration light and the stellar light simultaneously. And that typically gives you a factor of maybe between 30 or 100. So the differential shift between the two spectra is typically a factor of 30 or 100 less than the absolute shift of your spectrum on the spectrograph. And then you get into a range that you can build. So I take an example here of the CARMEN-S instrument with which I am very familiar, but other instruments work similarly. CARMEN-S is special in that it has two separate spectrographs. Most of the other instruments have only one, but that's a side issue here. So you have the spectrograph inside a vacuum tank. You have a front end that is attached to the telescope, and the two systems are linked with two fibers. And one fiber here is for starlight, and the other fiber is for calibration light. So there's a calibration unit that is also linked to the front end that sends calibration light up here. And having two fibers get into the spectrograph helps you to do this simultaneous calibration. Also, the spectrographs can be far away from the telescope in a much more stable environment. And of course, you have all kinds of control systems, cooling systems, interfaces, a GUI, and so on. Again, this is the near-infrared vacuum tank of the CARMEN-S instrument, and to show that you really make a big effort to keep everything stable. This is in a separate room that one can see here, away from the telescope. The instrument is as well isolated from its environment as you can get. The spectrum that you take then looks something like that. Here you have the individual Echelle orders. So this is one order, this is n+1, n+2, n+3, and so on. Here are the stellar lines. You see individual lines here. And this is the second fiber, in this case, carrying the light from a lamp. So this is a hollow cathode lamp that has sharp spectral lines, and the position of these lines are given by atomic physics, so they are supposed to be stable. But remember, the task is now to take these two spectra. There's the stellar spectrum, there's the spectrum of the hollow cathode lamp, and you want to measure a relative shift between those two spectra with a precision of 1/1000th of a pixel. That is the basic measurement principle. Okay. One other thing, by the way, that you can see nicely in this picture here is that each spectrum has these two slices. We talked about slicing the fiber image to gain spectral resolution, and that is visible nicely in the spectrum here. So lamps are nice in principle if you can expose your stellar spectrum and the lamp spectrum simultaneously. The lamp can be used to anchor the wavelengths. A big problem, however, is that the lamps have many lines that you would like to use for your calibration, but they also have a small number of extremely bright lines. And these lines really spoil the whole exposure. You can see here that the bright lines bleed over the spectrum. And so each one of these lines here, you can see the artifacts, really spoils a large section of the spectrum. So therefore, we are looking also for other ways of calibrating the spectra. And one attractive alternative is a Fabry-Perot etalon. A Fabry-Perot etalon creates these very nicely spaced and equally bright calibration lines. This is nice for calibration. The drawback is that a Fabry-Perot etalon by itself is not a fundamental wavelength standard. It is not tied to atomic physics, but it is tied to the kind of arbitrary separation of two optical plates. So if you use a Fabry-Perot, you have to tie that Fabry-Perot in some way to a fundamental frequency standard, which could be then a separate exposure with a calibration lamp, or there are other ways of providing a stable wavelength reference, for instance, a laser frequency comb. There's another requirement, and that is the input stability. So you can make your spectrograph very stable. If the input is not stable, you have a problem also. At each wavelength, the spectrograph creates an image of the slit on the detector. So if that image moves, this looks just like a radial velocity variation. So for instance, if you just take a spectrograph slit and put your spectrograph directly on the telescope, because of seeing, the illumination of the slit will vary with time, and that variation of the slit illumination looks like a radial velocity variation. And I mentioned this requirement of roughly 1/1000th of a pixel, or a fraction of 1/1000th of the slit width, and you basically never get a stabilization on the spectrograph slit that is that good. So here's where fibers comes in. Optical fibers have the nice property that the fiber output is always more stable than the fiber input. So here we have the input of a fiber, and the star position varies with time because, for instance, your pointing of the telescope is not quite stable, or because you have image motion due to seeing. Then you route the fiber to the spectrograph. This corresponds to a shift of the spectral line on the spectrograph. But because the output is more stable than the input, this shift is much smaller than if you had coupled the light directly from the telescope into the spectrograph. And you even can play tricks to make it even better. A round fiber, as I will show in a minute, does not give you a really stable output. It is much better than the input, but you can do even better by using either octagonal fibers or image fiber scramblers. So here I show the input and the output of a round optical fiber. So that is your standard telecommunications fiber. Here's the input, and this is from a lab experiment, a small spot created on the input of this fiber and moved from the center to the edge. And this is what you see in the output of the fiber. So you see it's much more regular than the input and rather symmetric, but the light still is not uniform, because a round fiber, because of its symmetry, has very good angular scrambling, but not so good radial scrambling. This is where, for instance, an octagonal fiber comes in, and this is input and output of an octagonal fiber. In an octagonal fiber, you do not have this spherical or angular symmetry, and therefore the scrambling is very good both in the radial direction and in the angular direction. So this demonstrates very nicely that you can easily move your input on the fiber. The output is very, very stable. So almost all of the precision instruments for the Doppler technique use either octagonal or square or some other type of non-round fiber, or another device, which is called a fiber scrambler, which reverses the angular direction with the position on the fiber input. I should finally mention telluric absorption, which is also a chapter in itself, which I think will be treated in other talks in this series. I just want to mention it here that this is an effect that affects the precision that you can get. You have many lines in your spectrum, especially if you want to work in the red and in the near infrared, that do not come from the star, but from the sky. And you have to disentangle the stellar spectrum and the sky spectrum, because otherwise that will also have a detrimental effect on your precision. So I will close this with a view graph about the challenges that are encountered if you want to do extremely precise radial velocity measurements. And I have color-coded them here a little bit with an admittedly subjective rating of what I think is quote-unquote easy and quote-unquote difficult. There's nothing that is really easy. There's no green in this view graph. But the basic physics, at least the photon noise, is very well understood, and you can relatively easily calculate that, and then you know where you can go if you do everything else optimally. You have to build a very stable spectrograph. You have to have stable coupling into that spectrograph. You have to have a stable and precise calibration and data reduction, which is not to be underestimated. And then you have effects that come from the sky and the stability of the star itself. So radial velocity variations or apparent radial velocity variations induced by stellar activity, by spots that rotate across the surface and similar effects. That is a very big challenge in the regime where you are in the meter per second or even sub-meter per second regime. And finally, the atmosphere imprints telluric lines on the spectrum, which are not completely stable and have to be taken out. So here I would like to thank you for watching, and I stop my presentation. Thank you very much, and also enjoy all the other presentations in this series. Goodbye.